Okay, the first part of this, I don't want to take very long because I really just want to get to the practice of this, but you do need some of this background information, so stick with me here through this first page. Couple things that you need to remember is that when you're talking about integration, or when you're talking about an integral, it's referring to the product of f of x and x. This is going back to the first unit when we did like counted boxes for the first time, and I think that's where we learned the trap rule as well. And we used integration at that point really to find distance, which is just accumulation of speed over time. So, but one of those things changes. So when we're talking about rate and time, when you multiply those together, you get distance because rate is the thing that varies. The integral is equal to the area of the region underneath the graph of whatever function you're looking at. And the ways that we've used this already to find, or the ways that we've used already to find this area, one of them you did today, which, I mean, very, very rough estimate is counting boxes. And then what was the other rule that we've already learned how to find this area?
Trap rule.
Trap rule. Okay, so today we're going to work with Riemann sums. Riemann sums is another type of estimation. So when you use Riemann sums, you're going to get a very close approximation, but you're not going to get the exact. And then we're going to review from the video yesterday how to get the exact. All right. So there's a lot of stuff going on here with k's and with f of c's and f of x's and da-da-da-da. But really all you need to notice here is in each graph you have a set interval that you're looking between. It's not just arbitrarily saying underneath this entire graph you're going to find an area underneath the curve. It's giving you a beginning point and ending point. So between A and B, find the area underneath the curve. And then there's three different approximations that you can take. If you make the rectangle's height the left point, or where the rectangle would connect with the graph on the left-hand side, that's called left-hand Riemann sum. If you take the middle between each interval, that's called midpoint. And then if you use the right-hand point of each interval as the height, that's called the right-hand Riemann sum. You can see that each one of these approximates the area, but the one visually that has the least extra and missing area would be which one?
The midpoint.
The midpoint. Okay, so you do need to know how to set up each one, but really all that changes between the setup is your heights, or where you take your heights at.
I have a question.
Hello?
I have a question on that. Well,
Good.
get to
I don't know offhand. I would assume that they would want them to be able to do that in the metric and the system. Yeah. Like whatever it's called, the one the one that we use, nobody else uses.
why don't you guys let me stupid question, but I think she might be making an exception for us sophomores that were eating there first. Because, like, Anthony, Kevin, Nick, and Lewis were eating there, and then they started eating in the library, and it was just us. And
I would
they're all
assume.
freshmen came, and they stopped cleaning up after themselves.
Mm-mm.
What they don't?
I mean, Jessica Roosh might be.
How does a woman
Yeah,
get
or
there?
Cole.
I ate the hard part. I left that. Actually, I think I left the first page in the
Okay.
library.
Alright.
Did you leave your too? No. I don't
Sorry.
think so. Could you get his?
Alright. Let's pull it back.
The library person.
Mhm.
I
finish my thought first and then you can ask your question. Is that okay?
Yeah.
Okay. With this blank here, really all this paragraph is talking about is the setup of each one of these types. But the area of any one of those rectangles, which you've already done, how do you find the area of a rectangle?
Length times height.
Length times width, which in this case, the length is considered the height of the rectangle. It's like taking these and setting it outside. That's the length, and then that's the width. Okay. So to set that up, the area would be f of c sub k, and all that refers to is the y value, or the height of the rectangle.
Is that an A or an H?
It's a k.
No, the first letter.
F A equals f of
Area.
that.
See,
Okay. And then if that represents the length, then what represents the width? In all these,
X.
an x, and since x is going to change, or the value of that's going to change every time, we're going to write that as change in x, or just some space of x. Sometimes with Riemann sums, your space or your x's that you're multiplying by, your widths that you're multiplying by, differ. They're not uniform across the whole thing. There might be one width that's 2, one width that's 1, one width that's 3, so you have to know how to set up. Yeah, TJ.
If it's all one uniform width, what's that?
We're getting there.
And also, are there infinite integrals?
Yeah. That's kind of.
What happens if you're trying to take the integral of something that's below the x-axis?
We will get to that when we get to area and volume.
Okay.
Because it does come into play. Usually it's looked at as negative area, and then we subtract it. Like if you're talking about distance, it's like going backwards. Yep.
So then theoretically, the integral from infinity to negative infinity of, or wait, negative infinity to infinity of just the line x would be 0.
Sure.
Because it's negative from
Mhm.
the side of the axis.
Yep. All right. So a definite integral is defined in terms of the Riemann sum. The symbol that's used for this, which if you watched the video last night, which you should have, you've seen this symbol. It's the same as an indefinite integral, but a definite integral means you can find an exact answer. Now, with Riemann sums, we're going to use them to find approximates. But then when the video and what we're going to review today, we're going to find exact. The A and the B here refer to the intervals, like where your integration will begin and where it will end. All right, go and flip. Okay, the mathy definition of a definite integral starts out like this. You have to, in order to have an exact area underneath the curve, you have to have a beginning point, ending point. Otherwise, it's just infinity, and you're not sure where to begin and end, and it's hard to add stuff up when you're not sure where to stop. So they do have to give you a beginning and an end. But as everything we've done refers back to limits, essentially a definite integral. Now, that doesn't mean you have to take the limit of a Riemann sum every single time, but when you find the exact value of an integral, you are finding the limit of a Riemann sum as your change in x approaches 0. Now, change in x referred to what with each of these triangles or rectangles?
Width.
The width. So it's saying as the width gets smaller and smaller and smaller. Well, if the width is getting smaller, what's happening with my rectangles?
They're
They're
moving apart from
increasing
each
in
other.
number.
They're what?
Area is
Decreasing in number.
Their
Area is decreasing.
area is decreasing? Not really.
Oh, there's more
The
rectangles.
total
There
area
you go.
is
Yeah.
decreasing.
Some of you have said that there's more rectangles. In order to cover the same amount of area, if your width is getting smaller, that means your rectangles are multiplying. So as your rectangles multiply, is the area extra and that you're missing, is that going to decrease even more?
Yes.
The more rectangles you have, yes. Okay. So that's what it's getting at, is that the exact value is taking the limit as your change in x approaches 0 of your Riemann sums. So this refers to Riemann sums.
Is that R of H or K?
R of n.
Oh. What? Sorry, dude.
Okay, so as your increments get smaller, and increments being like the width of your rectangles, your area of the rectangles gets closer to the actual value. Okay, and then we're doing one example with this, because pretty much one example is all we're going to need. And we're going to look at the integral from 1 to 4 of the function 1 over x dx. Now, this does not mean we're going to integrate this by hand. Okay, so for the integral listed here, we're going to find L sub 6, U sub 6, M sub 6. Now, this is how it's going to usually be written for Riemann sums. What do you think the L sub 6 means?
Left.
Left-hand Riemann sum. U means
Middle.
No, that's
M means middle.
Left.
U means
Right.
the right,
Why not
but
left?
it's called U because they sometimes call the right-hand Riemann sum the upper Riemann sum.
Wow.
So I use those because that's how it's going to pop up, I think, in your book.
So then the L can also stand for lower?
Yep.
Oh, snap.
Okay, so we're going to set up the L sub 6 first.
What's the stuff on the
I
left?
think I missed some.
L6.
Oh, duh. Okay, so we have L sub 6. Now, what do you think the 6 means?
Number of
value of
increments.
rectangles.
Number of increments or number of rectangles we're going to draw in, right?
Yep.
Alright, so
Or not.
I will graph this eventually, but I'm not going to graph this right off the bat. In order to figure out what your uniform width is going to be for all your rectangles, you have to look at how much space you have to work with. How much space or units are between 1 and 4?
3.
There's 3. So I got to fit 6 rectangles in a space of 3. How much width is going to
That
be?
is going to be 0.2.
Should be 0.5.
I'll do that.
Because you take 3, and maybe you want to do this kind of off on the side here. To find change in x, you're going to divide 3 by 6 in this case. Or the amount of space you have, or units, divided by the number of rectangles that they want. So if I wanted L sub 12, then I would divide 3 by 12, and each width would be 0.25. So it just depends on how many rectangles they want. Okay, so my change in x is going to be 0.5. Now, because every width of my rectangle is going to be 0.5, I'm just going to write it once. Kind of like what we did with the trapezoidal rule, is we wrote the width once, and then just multiplied everything by it at the very end. And then inside the parentheses, I'm going to put all of my y values, or all of my heights. Okay, so this is going to be my change in x, or my width. And then all this in here is going to be the heights of my rectangle. Now, if we're looking at L sub 6, that means I'm going to have the left-hand point or the left height of each rectangle. Which means the x value that I plug in for my height, for my first height, is going to be 1. And actually, you know what? I might want to graph this really quick. I'm just going to graph it on mine. You don't have to graph it on yours. I just think maybe a picture will help.
I have a question.
Yep. Go ahead. What's your question? plug them into the equation? Okay, so I put in my function. I went from 0 to 5, but the area we want underneath the curve is that area right there. So I'm going to zoom in just a little bit. So I want this area underneath the curve. Okay, so everybody follow me there? So my first rectangle is going to be, let's see if I can actually draw it in. So the height of each of my rectangle, and I know I didn't draw them all, but the height of each of my rectangles for L sub 6 is going to be the left height of my rectangle. So I'm going to plug in 1 to find the height of my first rectangle. What x value do I have to plug in to find the y value of my second rectangle? 1.5, and then 2, and then 2.5, and then 3, and then 3.5, and then that's it, right? Because if I plug in 4, that's the right-hand side of that last rectangle that I need. So I'm going to do f of 1 plus f of 1.5 plus f of 2 plus f of 2.5 plus f of 3 plus f of 3.5. So if you need some notes here, this represents the x value that you're plugging in. This is the height. Okay. Now to find those actual values, I think Tina's the one who brought it up, we're going to have to plug that back into the original. So since I already put my function into the calculator, I'm going to go to my table and actually put in those values. So 1, 1.5, 2, 2.5, 3, 3.5. And those are the decimals that I would need to put in there. Okay? So I have 0.5. F of 1 is 1. F of 1.5 is 0.667. F of 2 is 0.5. F of 2.5 is 0.4. F of 3 is 0.333. And f of 3.5 ends up being 0.286. Okay, so these are just punching out the y values at those given x's. And then my L sub 6, if you have a calculator near you, if you would start adding up those decimals and then multiply by 0.5 for me. And as soon as you get that answer, raise your hand so I can check your work.
Okay, you
What
got
you got?
1.4.
I got 1.593.
I got
1.593.
1.593?
I know what it is.
It should be 1.593. And since this is an area underneath the curve, we're going to put units squared there to represent area.
492.
Not sure. We're just adding up decimals and then multiply by point. Make sure you're multiplying by 0.5. Maybe that's what happens. Okay. Then we're going to do u sub 6. Is my width going to be the same?
Yes.
Yep, because I still need 6 rectangles. But the x values that I'm plugging in, they're going to be
1.5.
they're going to be different, right? They're not going to be the same set that I had before. Because now, if we were to look back at my graph, instead of picking this as the height for my first rectangle, I'm picking that as the height, and that as the height, and that as the height. So you're picking the right-hand side of each rectangle as the height. So what is that x value then for my first rectangle?
1.5.
1.5? and then f of 2, then f of 2.5, then f of 3, f of 3.5, and where do I stop? F of 4. Now, you can always double check. You should have 1, 2, 3, 4, 5, 6 y values listed there since you have 6 rectangles. So just make sure you have 6 values there. And then I have some of these listed already. So 0.667, 0.5, 0.4, 0.333, 0.286, and then f of 4 is 0.25. So use sub 6. Again, if I could have 2 or 3 people punch this out.
I thought we didn't like decimals.
1.218.
Yes.
Well, this is an approximation, so we're okay.
When do you not use decimals, and when do you use decimals? Because when are you supposed to?
You use decimals when you have decimation, use fractions when you have fractions.
Are you talking about this part or this part?
Like, because I mean, this is easy enough that you could like use fractions, and I thought that you will use fractions when you can, and punch
You
it out
could
because
you could use fractions. I would with Riemann sum stuff, they're more lenient because it's an approximation.
do they expect you to always punch it out to a decimal?
Yeah.
TJ, what's 0.285
Okay.
and what is this actually?
We're gonna set up m sub 6 together.
286.
What sub? 276.
Okay, let's go with Chelsea. What's my width gonna be for m sub 6? The same as the other two. Good, because we still have to fit 6 rectangles in, so the width's gonna be the same. And then here's the tricky part. What x value do I have to plug in to represent the midpoint of each increment?
1.25.
1.25. Good. Because the first rectangle goes from the value of 1 to 1.5, so halfway in between would be 1.25. Then what would be the next one?
1.75.
1.75, because that's halfway in between 1.5 and 2. And then 2.25, 2.75, 3.25, and 3.75 is our last one. Again, if you're not sure if you have them all, just count 1, 2, 3, 4, 5, 6. Okay. On your own, or with your table or whatever, if you could find those y values, you might want to use your table feature of your calculator, because it's probably the quickest way to do it. And plug those in.
Whoever uses change the y to r into like a 1 or a r.
Can you do riemann sums in a calculator by using the summation thing?
We're going to do that next. Okay, do we have any answers quite yet?
For f of 1.
Connor, you have something?
Yeah. For 1.25, 0.8.
And then the next one should be 0.571.
And then 0.444.
what we should have. Taylor? 1.377? Good. Units squared. So all of these should be close, right? And you can see that the midpoint value is in the middle of the other two, which is going to happen most of the time. And out of all three, this is probably the best estimate. All right. Grab a calculator that has the trap rule on it, and if it has the trap rule on it, you should also see the rule Riemann. We're going to run through how to use it on the calculator as well. You do have to know how to start over. You do have to know how to do it by hand, like we just said, but also do it on the calculator. Go to program.
Nobody's gonna have it anyway.
Yeah, we don't have time to put it on today if you don't find one, but if you can find one in the next minute or so. If not, just follow along because it's going to be easy to use, especially since you use the trap rule already. There's just a couple quick things that we have to figure out. Okay, so if you have a Riemann sum program, and if you don't, we'll get you loaded up here tomorrow.
No, I don't have one.
You would run the program.
Oh wait.
What's the A in this problem?
1.
The A is the beginning interval value, which is 1, right? Because we're going from 1 to 4. So A is 1, B is 4. The other thing that you do have to make sure that you've done, already, is make sure that you put your function into y equals, which I know I have already done, and probably you have too, but you would have to have the 1 over x, otherwise it's not going to know what function to use. What's the n?
0.5.
N is the number of rectangles.
6.
So this is going to be 6. Now, PCT means percentage. This is how this program has to work. 0 percentage means left hand, Riemann sum. 50 percentage means midpoint. And 100 percentage means right hand. Okay? So we're going to go midpoint. So I'm going to select 50. And do I get 1.377? Yep.
Do you have a place to put that batteries?
We just throw them away.
Trash.
We used to recycle, but now they don't take batteries anymore for recycling.
I did not hear that part. All I heard was dead, so I was like, what?
I bet. Okay. Now, if we wanted to make this approximation, closer to the actual, what would I have to change in the program?
Your
Number of
My n.
Yeah.
So let's say I wanted a better approximation. I'm going to go 100.
Oh.
Yeah, put it. Oh.
Midpoint. Runs for a while.
A long time.
Not a super long time. Because it has to calculate all the different.
Boom.
And we get something that's really similar, right? 1.38. It's close, but it's actually a little bit closer.
What's the really big number?
What?
What's the
Oh, it's the 46.
Yeah.
This is all the areas of the rectangles without,
Multiplying.
all of them added up without multiplying by the increment.
It should be 0.5.
Okay. Well, except it's not 0.5 anymore because you have 100 rectangles.
Oh, okay.
So it's 3 divided by 100. So it'd be 0.003.
Fair enough.
All right. If you would put your notes away.
Don't forget.
I'm going to review.
Oh, did you get your secret epic calculator that has the phone?
Hold on, that's not what we're talking about right now. We're going to review one problem together here. So grab a whiteboard or grab just a piece of paper or just watch, because this is not going to take very long.
Sure. Still going?
didn't watch the video last night, you will want to make sure you do, because even though we'll review like particular solutions and differentials tomorrow and some in the video tonight, it would be good to make sure you do that. But this is the main thing that we talked about last night, which was the fundamental theorem of calculus, which is basically making an exact answer and not an indefinite answer anymore. So this is going to use substitution. And Brad, what would I let U equal here?
X cubed minus 1.
Okay. And then my du would be 3x squared dx, correct? I don't have a 3 up here at all, so I'm going to have to move that over. So I'm going to replace x squared dx with 1/3 du. And then I'm going to rewrite it. So you should have 1/3 u squared du after you do your substitution. If I integrate this the way it is, I'm going to add 1 to the exponent and divide. So what's the fraction I'm going to get if I do that? What is it? 1/9 it should be. Now I'm not going to put the plus c here because I have my limits of integration, or where it wants me to find the area between. So if you watched the video last night, we identified that after we integrating, we draw a straight line. This is just notation that they use in many textbooks. So draw a straight line and put your limits of integration. Now I can't plug in 4 and 0 here because essentially at the very beginning these are x values, not u values. So I have to first replace what u is and then integrate from 0 to 4. Now, not integrate, and then evaluate from 0 to 4. When you evaluate, it's basically taking 4, for the number on top, plugging it into your original function, because now that we've integrated, this is my original function, and then you subtract f of a. This is considered a, this is considered b. So you do f of b minus f of a, plug in 4. If I plug in 4, I get 63 cubed divided by 9,
7 actually.
which is what? 7d? 7?
I got
63 cubed?
really,
No,
really.
oh, it's cube, never mind.
I got him cubed 27,783 and 1/9.
Just put 2783.
Okay, so I get this number when I take 63 cubed and then divide it by 9, which is what I get when I plug in 4. And when I plug in 0, you end up getting what?
0.
Well,
You
no.
get
You get
one
negative 1,
Oh.
right? And then negative 1 times 1/9. So you'd be subtracting a negative. So really you'd be adding. So we'd be adding 1/9. So you get this decimal, which would be a fine answer. Or if you want it as a fraction. Just kidding. It's not letting me write it as a fraction. You'd have to get common denominators, but probably that's the answer that they'd be looking for. Would be 27,783.111. Now, why this is useful is because now this answer represents the exact area underneath the curve between 0 to 4. So before, when we had to count boxes, use rule and sums, now we can just jump to the exact answer if we're able to integrate. Okay. I think we need to put away the whiteboard because at this point, I want to see where we're at